Hi everyone, welcome back to chemistry. Today we're going to start Unit 5 on the periodic table, and you're going to learn throughout this unit and even beyond this unit that there are many trends in our periodic table that make it a very useful tool for us. So first off, the elements. The names of the elements on our periodic table come from a variety of places. Some of them were known to the ancients, such as sulfur, tin, carbon, and copper. Others come from places. They were named based on the places where they were discovered, such as francium, polonium, germanium, etc. Some are named by famous people. Einsteinium, obviously by Einstein, fermium, etc. Others were named based on the foreign language that people who discovered them spoke. So W is tungsten, which we probably would never guess if we didn't know that, because it was discovered in Germany and it came from a mineral that they named wolfram, and that's where the W comes from. Fe is iron, ferrous, Au is gold, etc. Some come from mythology, and then others are related to the properties of the element. So mercury is Hg because it stands for hydrogyrum, which is Greek, and that represents the shiny surface. Dobereiner did some early work on organizing the periodic table around 1830. And what he did is he organized the elements into groups of 3 that were called triads that have similar properties. So those elements eventually evolved into different families. So as you can see in the picture, lithium, sodium, potassium, which are in red on the left in the table there, those are currently what we call the alkali metals or the alkali metal family. Calcium, strontium, barium is the alkaline earth metal family. We now know them as families, but his early work on grouping them into 3 started off this organization that we have. Then in around 1865, John Newlands did some early work as well, and he decided to organize them based on relative atomic weights. So what he noticed when he arranged a table on relative atomic weights was that each element was similar to the element that was 8 places ahead of it. He noticed this, however, there were lots of discrepancies with this, so it didn't stick around very long, his idea. And then came in 1870 or around 1870, Dmitri Mendeleev, who is given credit for the periodic table. We now refer to him as the father of the modern periodic table. And he organized the periodic table by increasing atomic mass. And what's important that he did is he left spaces and predicted properties of undiscovered elements. So Newlands before him had those discrepancies that made people not believe his table, but Mendeleev, when he organized the table by increasing atomic mass, left spaces, and later on people discovered elements that had those properties that he predicted. And then Meyer, unfortunately, was a little too late to the game because he published his own table months after Mendeleev when people were already buying into Mendeleev's table. Moseley, however, because if you look at the periodic table right now, you'll notice that yes, it's generally in increasing atomic mass, but not always. For example, if you look at atomic number 52, tellurium, and atomic number 53, iodine, please have your periodic table next to you during this entire screencast. You'll see that tellurium has an atomic mass of 127.60. Iodine, however, has an atomic mass of 126.9045. So the atomic mass is not increasing between those 2 elements. If you look closely at the table, you'll see other similar examples. So Moseley then decided to put elements in order of increasing atomic number, which is how our periodic table is organized today. It's based on increasing atomic number, not increasing atomic mass. Then fast forward to the 1940s, Glenn Seaborg developed the actinide concept, which led us to the current arrangement of our table, where we have our F block underneath the rest of the table. He also discovered or co-discovered 10 elements. So we do have an element named after him. It's atomic number 106, and it's called Seaborgium. The periodic table has embedded into it periodic law, and that just means that the properties of the elements repeat themselves every so often. So a period, like we've said before, is a horizontal row, and we have 7 periods on the periodic table. A group is a column, and we sometimes refer to our groups as families, as I mentioned earlier. So we have 18 groups on the periodic table. And then, as I said before, group 1, for example, is known as the alkali metals, although hydrogen is not part of that family, even though it's in the same group, and I'll talk about that later on. So let's look at some patterns and some charge trends. If this is our periodic table, we've talked about the S block on the left, the P block on the right, the D block in green here in the middle, and the F block below. So you already had to memorize that group 1 will form ions with a charge of +1, group 2 is +2, 13 +3, 15 -3, 16 -2, 17 -1. That we had to memorize last unit. In the middle, we kind of skip those because their charges will vary. We don't have a pattern that they always follow, so we kind of skip that. Sometimes iron will have a +2 charge, sometimes it'll have a +3 charge. Copper sometimes is +1, and other times it's +2. That red line that was just drawn in is our staircase, or our metalloid line. All the elements that touch it are metalloids except for one of them. To the left of the staircase are our metals, except not hydrogen. So you can see right now that hydrogen is changing to pink in the top left corner, because hydrogen, even though it's on the left side of the staircase, is not a metal. The right side is our nonmetals, including hydrogen, as I just said. And then everything touching the staircase is a metalloid, except for aluminum. So aluminum is right here on the periodic table, and that is not a metalloid, it's a metal. But everything else touching the staircase is a metalloid, which means that it has properties similar to metals and nonmetals. All right, alkali metals, like I said, that's group 1. Every element there except for hydrogen, they will all form a +1 charge, and they are very reactive. Alkaline earth metals, so these are the family names, and you need to memorize these family names. Our group 2, they will all form a +2 charge when they form an ion, and they're not as reactive as the alkali metals. The halogen family is group 17. They will all form a -1 charge, and they are very reactive. Noble gases is group 18. They don't form ions, so they won't have a charge because they're going to stay neutral. And they are not reactive because, remember, they follow the octet rule, or helium has a full outer shell, so they don't want to react with anybody. They're very happy as they are. Lanthanides are at the bottom of the table. Those are elements 57 to 71, so those are the top row of our F block. Notice that element 57 is called lanthanum, so they start off the lanthanides. The actinides are right below that row. Those are elements 89 to 103. If you look at element atomic number 89, you will notice that the name of that element is actinium. So again, those are in the F block. The coinage metals are found in group 11. So if you look at your periodic table, you'll see them. Those are copper, silver, gold. The transition elements are going to be our D block, as we like to call them, or groups 3 through 12, and as we already said, they will have variable charges. The main block or representative elements are going to be groups 1 through 2, and then 13 through 18. So essentially that's our S&P blocks. So let's kind of organize this by looking at the table. So here's our periodic table. Group 1 is our alkali metal family. So that's everything in red. Notice that the element hydrogen is not in red because it is not part of the alkali metal family, even though it's in group 1. Alkaline earth metals, as we just said, are group 2. Halogens are group 17. Noble gases are group 18. The lanthanides are in the F block, the top row. Actinides are the row below the lanthanides. Coinage metals, those are the 3 I mentioned, copper, silver, gold. Transition elements are all the ones in yellow, including the coinage metals. So everything in your D block is called a transition element. The metalloids touch the staircase, except not aluminum. And then the ones we haven't colored in to the right of the staircase are nonmetals, which we already talked about. And then to the left of the staircase, which we haven't colored in, are metals. The main blocks, like we said, are groups 1 through 2 and then 13 through 18. So if an element has the same number of valence electrons as another element, that means they're going to have similar properties to each other. Because these valence electrons are responsible for chemical bonding, as we said in unit 4, the last unit. So they're going to have similar properties. Let's look at lithium and sodium, which are both in group 1. Lithium's in period 2, sodium's in period 3. Here is the electron configuration for lithium. And we look at the highest energy level, which tells us how many valence electrons there are, and we see that lithium has 1. Sodium, here's its electron configuration. Highest energy level is the 3rd, so we see that there is 1 valence electron there as well. So they have the same number of valence electrons, so lithium and sodium will have similar properties to each other. In any group, the element below has 1 more occupied energy level than the element above. So lithium occupies energy levels 1 and 2, so the highest is 2. Sodium occupies 1, 2, and 3 energy levels, so the highest is the 3rd energy level. So as you go down the group, that pattern will emerge. So there's lithium, and then you see sodium with an extra energy level. So the period that an element is in, so lithium is period 2, is the same as the energy level that its valence electrons are in. Sodium's in period 3, so its valence electrons are in the 3rd energy level. Below sodium is potassium in group 1. Potassium's in the 4th period, so its valence electrons are in the 4th energy level. So like I just said, lithium, 2nd period, 1 valence electron in the 2nd energy level. Sodium is in the 3rd period, 1 valence electron in the 3rd energy level. EL there stands for energy level. Periodicity. These are the trends in properties of the elements. So you've got to know these, and we refer to these trends and periodicity throughout the year, so you've got to pay attention, make sure you understand this, and if you don't, please ask for help. So we have trends when you go from left to right across the table, and also we have trends when you go from the top to the bottom of the table. So when you go from left to right across the table, those trends will result from Coulombic attraction, which is the attraction between protons and electrons. When you go from top to bottom, those trends result from layers of electrons, right, in each of the energy levels, and what we call the shielding effect. So let's talk about each of those a little bit more on the next couple slides. Coulombic attraction depends on 2 things. It will depend on the amount of charge and the distance between the charges. So those two things. Now this might sound familiar to you, to universal gravitation, which you talked about last year in conceptual physics probably, where we said that gravity will depend on the mass of two objects and how far apart they are from each other. So that's why you and the person next to you will have some attraction, but your masses aren't very large, so it's not like you're being pulled towards each other. Versus you and Earth, Earth has a large mass, and that's why you can stand foot on Earth, because of that large mass and the distance between you and Earth. So it'll depend on the amount of charge and the distance between the charges. The more charge there is, the greater the attraction. So you can kind of see that by how thick those arrows are. The more charge, the greater the attraction. And then the closer those particles are, the greater the attraction. So let's say we have two carts, one on the left, one on the right, held together by some spring. The one on the left contains positive particles. The one on the right contains negative particles, or we could say protons and electrons. Let's consider lithium. Lithium is atomic number 3. So a lithium atom, remember, anytime we talk about atoms, they're always neutral. And if we don't tell you, by the way, then you assume it's neutral. It's only when you see a charge that you know that it's not neutral. Lithium has 3 protons, so it has 3 electrons. And notice, compared to the red carts above it, these carts are closer together because there's more charge. Beryllium has 4 protons and 4 electrons, and it's even closer together than lithium. So the more charge there is, the closer or the greater the attraction between these things. So as you go across the periodic table, so this arrow here is telling you across the periodic table from the left to the right, there is going to be more Coulombic attraction. Because there is no new energy level, there's going to be more pull, making the atoms get smaller in size, which might not be what you would have expected, right? Because as you go across the table, you're thinking, oh, well, I'm adding a proton and an electron every group I move over. So why would it not be getting bigger? Instead, the atom is getting smaller. So we could say maybe this is lithium, beryllium, boron, carbon. You might think those should be getting bigger. There's more protons and more electrons. However, because there's more charge and there's no new energy levels, because if this is lithium, beryllium, boron, and carbon, the highest energy level for all of them is the second energy level. So with more charge, it can pull in closer to each other. Those electrons are attracted to the protons. So they can get closer and closer as you add more protons and electrons. And so therefore, the atomic size will get smaller as you go across the period. So that was Coulombic attraction. Let's talk about the shielding effect. That's where our kernel or core electrons will shield the valence electrons from the attractive force of the nucleus. So remember, the nucleus has an overall positive charge. There's no electrons in there. The neutrons don't have any charge, so it's an overall positive charge. And these electrons are negative. Opposites attract. Well, if you have a lot of non-valence electrons, so a lot of electrons between your nucleus and your valence electrons, they shield that attractive force between the valence electrons and the nucleus. Because remember, the valence electrons don't want to be near other electrons. So those are our valence electrons. It's going to be easier to remove a valence electron from potassium than it will be from lithium. And the reason is because those core electrons, the kernel electrons, repel the valence electrons. So the more core electrons there are, the easier it is to remove that valence electron from that atom. So as you go down a group, your shielding effect increases. because you add an extra energy level every single period you go down. So every time you add an energy level, you're adding more of these electrons at a farther distance from the nucleus. So atomic radius, the definition is just the size of a neutral atom. As you go down a group, so as we go, the arrow there going down means we're going down a group, the atomic radius is going to increase. And that's because we're adding a new energy level each time. Let's say we have hydrogen. This is the relative size of hydrogen. Then we add an energy level. Now it's lithium and it's bigger. Sodium's even bigger. Potassium, etc. As you go across a period, the atomic radius will decrease, and we said that is going to be due to the Coulombic attraction. So once again, as you go across a period, you are in the same highest energy level the entire time you go across the period, but you're adding an extra proton and an extra electron every group you go across, and they're going to have a stronger attraction for each other. Okay, there's more charge, so there's going to be a stronger Coulombic attraction. So that is your trend for atomic radius. As you go down a group, the atomic radius increases. As you go across a period, whenever we say across, it's always left to right. As you go across a period, the atomic radius decreases. So here we can see some examples from groups 1, 2, and then 13 through 17. So if we look at period 1, which contains lithium, beryllium, boron, carbon, etc., you can look at the numbers below, like 1.52 below lithium. That's just the size of a lithium atom measured in angstroms, which is a unit of length or distance. And then beryllium, the actual size of a beryllium atom is 1.11. So you see, those are actual numbers. Those aren't made up numbers. You see that the size is getting smaller. Here's a different way of looking at the same information. So if we look at, let's start with period 2 because it's a little bit more obvious. So if we look at period 2, we have atomic radius on the y-axis, atomic number on the x-axis. So in period 2, we start off with, sorry, that's period 3 I circled. In period 3, we start off with sodium. Then we go down to magnesium. So that's the atomic radius of magnesium, which is smaller than sodium. Then aluminum is even smaller. Silicon, till we get to chlorine. So we see that the general trend across that period is the atomic radius is getting smaller. That's true for period 2. That's also true for period 2, period 4, etc. So this is period 2, period 3, period 4. Now you'll notice if you look at period 4, there's a little blip here. So it's not perfect, this trend, like it's not going to be exactly increasing every single time. There will be some anomalies for different reasons, but the general trend will stay the same. Ionic radius, as you might guess, is just the size of the ion. So cations, remember they form positive charges. If we look at calcium, it's atomic number 20. A calcium atom will have 20 protons and 20 electrons. It's in group 2, so it's got those 2 valence electrons that it would really rather try to get rid of, because remember all these atoms, almost all of them want to follow the octet rule and have the same electron configuration as the noble gases. So calcium would rather have the electron configuration of argon. So what it will do is it will lose 2 electrons. So there's your calcium atom. It becomes an ion because that's more favorable. It will still have 20 protons because if it didn't, it wouldn't be calcium anymore. But now it would have 18 electrons because it loses 2 to have an electron configuration similar to argon. When it loses those 2 electrons, it's going to get smaller. So relative to its neutral atom, it is smaller. So you can make the general statement that cations are smaller than their neutral atom. Now let's look at anions. And remember, I told you in a different screencast that when you see what looks like maybe a capital I or a lowercase l after a capital C, 99.9% of the time, that's chlorine, not carbon and iodine. So let's look at a chlorine atom. Chlorine is atomic number 17, so it has 17 protons and 17 electrons. It wants to have the same electron configuration as a noble gas, and the one after it is argon, so it really wants to gain just one more electron. So it will gain an electron and have 18, and because it just got another electron, it's going to be bigger than its neutral atom. So we can make the general statement that anions are going to be larger than their neutral atom. So when you're in the same period, so notice down here we have same period, as you lose more electrons, just like our cations do, we get smaller. So in the same period, a +3 ion is going to be smaller than a +2, which is smaller than a +1, which is smaller than something that doesn't have a charge in that period, like the noble gas, which is smaller than a -1, etc. Okay, so that's for the same period. The positive charges, the bigger the number of the positive charge, the smaller it is. And then for the negative charged ions, the bigger the number, the bigger it is. All right, so let's do some comparing. So for each of the following sets of atoms, list them in order of increasing atomic radius. So our first set here is strontium. So there's strontium in purple on the periodic table. And then magnesium, there's magnesium. Barium, it's filling in, and beryllium. So we've got those 4 elements. Notice they are all in group 2. They are all part of the alkaline earth family. So we know that as we go down a group, we already said that the atomic radius increases. So at the bottom of your group, you have a bigger atomic radius than any element above it in that group. These elements are all in the same group. So the smallest one is the one on the top, which is beryllium. Then below that, look at your periodic table, is magnesium, then strontium, then barium. Let's look at the next set, group B, cesium, polonium, radon, and lead. Pb is lead, by the way. So here's cesium, polonium, radon, lead. They all were highlighted in red on the periodic table above. So we know that as we go across the period for atomic radius, they get smaller. So the one on the left is cesium, that's the biggest, and the one on the right is radon, that's the smallest. So radon is first, then polonium, then lead, then cesium. Last group, group C, we've got rubidium, which is there on the table, fluorine, calcium, silicon. Now, these elements are in different periods and in different groups, but think of our trend. We said as you go across the table left to right, the size decreases, and as you go top to bottom of the table, that the size increases. So because of that trend, we can say that the smallest radius is going to be fluorine, then silicon, then calcium, and then rubidium. Now, for each of the following atoms, determine the ion each atom will form. So strontium, magnesium, barium, and beryllium, we just saw, are all in the same group. They're all in group 2, so they all form an ion with a +2 charge. Right? Those are all in blue right now on the periodic table. So those are all +2. Potassium, selenium, and krypton are in different groups. So potassium's in group 1, so it's +1. Selenium is in group 16, so it's -2. And krypton is a noble gas, so it's 0. Last group, fluorine is in group 17. It's a halogen, that's -1. Sulfur is in group 16, that's -2. and aluminum is in 13, which is a +3. Now let's rank the ions in order of increasing ionic radius. So here, earlier we did atomic radius, now we're gonna do ionic radius. So we already figured out what ions they will form. These are the same groups, A, B, and C from the prior slide. They're all gonna lose 2 electrons, so their ionic radius will be based on the energy levels of the electrons. Keep in mind, as you go down a group, we're increasing in energy levels. So we kind of made a table here. We've got the beryllium ion, magnesium, strontium, and barium ions. They are listed in the order they would be on the periodic table. Beryllium's above magnesium, which is 2 spaces above strontium, which is above barium. So we can see how many protons they have, how many electrons they have, and then their highest energy level. So based on this, you should notice that beryllium is going to be the smallest, right? And then as we go down the group, it gets bigger. Let's look at the next group. Potassium, the potassium ion, the selenide ion, and krypton. So if we look at their configurations, those are the configurations when they're not ions. When they become ions, their electron configurations will change. We're going to focus on electron removal here. So when potassium loses an electron, it no longer has an electron in the 4s energy level, so it's just argon. Selenium will gain 2 electrons. So before it had 4 in the 4p orbital, but now it has 6. And krypton didn't change, right? Because it doesn't want to form an ion. So when they become ions, we notice that they have these electron configurations. So potassium, if we look at the table to the right, potassium has 19 protons, 18 electrons. That's the potassium ion. The selenide ion is going to be bigger. It has 34 protons and 36 electrons. Krypton has 36 and 36. So the selenide ion has the same number of electrons as krypton. We can see that in the table. But there's less protons, so therefore there's a weaker attraction and it's going to be larger, right? If your attraction isn't as strong, then you can't hold on to those electrons as tightly, so it will not stay as close, so it gets bigger. So the K plus, the potassium ion, is going to be the smallest. Then krypton, because it has more protons than the selenide ion does, and then the selenide ion. Last group, those are the electron configurations when they're neutral atoms. Let's focus on the electrons that get removed. So when they become ions, we notice that fluorine now has an extra electron in the 2p orbital. Sulfur has gained 2 electrons in the 3p orbital, and aluminum has lost 3 electrons. So here's our table again, and we see here that aluminum has more protons than electrons. So that positive charge is going to be a lot stronger because it can pull in 10 electrons. When there's 13 protons, that's strong attraction for 10 electrons. So aluminum is going to be the smallest, and then our fluoride ion, and then our sulfide ion. Next, let's look at ionization energy. So what that means is how much energy it takes to remove an electron from an atom. So if we have this generic equation, we've got M, which is going to represent metal, and then first ionization energy. So you put in some energy and you're able to remove an electron from the metal. So once you remove an electron, your metal now has a +1 charge and you've got this extra electron. Well, sometimes you're going to want to remove, or sometimes it's going to be easy to remove, a second electron. So if we take our cation, bring it down here, and let's say we have enough energy to remove a second electron. So the second ionization energy is how much energy it takes to remove a second electron. We end up with a metal with a +2 charge and yet another electron. We could maybe even do this a third time. We take our M2 plus cation and we put in enough energy to remove a third electron, and we get yet a third electron. So each successive ionization will require more energy than the prior one. Every time you try to remove an electron, it's going to take energy. So as you go down a group in the table, the first ionization energy will decrease. That's due to the shielding effect. So remember that as you go down an energy level, that means you're going to have a higher energy level, and there's going to be more core electrons shielding the valence electrons from the positive nucleus. So the more shielding there is, the less energy it takes for another atom to pull away that one valence electron. As you go across the table, the first ionization energy will increase. The reason it increases is because, remember, as you go across a period, you add an extra proton and electron every time you move over one group. Well, remember, there's that stronger attraction between those protons and electrons due to the Coulombic attraction as you go across a period. So because there's a stronger attraction, it takes more energy to remove one of those valence electrons. So remember, the shielding effect is when those kernel or core electrons shield the valence electrons from the attractive force of the nucleus. So when there's a lot of shielding going on, like on the right side with the potassium atom we're looking at, it's going to be easier to remove this valence electron. It's not going to require as much energy. When it's easier to remove, that means there's less energy needed to put into it, right? It's like if you try to push a heavy desk versus a light chair, a lightweight chair, like the easier it is to push it, the less energy you have to use. But when it's tougher to remove a valence electron, like with the lithium atom on the left, it's going to require more energy. So as your shielding effect increases, the amount of ionization energy needed to remove an electron will decrease. So as there's more shielding going on, like on the right picture, there's less energy needed to remove an electron. As the shielding effect decreases, the ionization energy will increase. So when there's not a lot of shielding going on, there's going to be a strong attraction between your valence electrons and your nucleus. So it's going to take more energy to remove a valence electron. All right, so you might need some of these numbers on this table for your practice problems. So please refer to this table when you're doing them. Let's just look at the atomic numbers in the first column. We've got atomic numbers 1 through 20, and then their symbols. And let's look at some patterns here based on what we talked about so far. So we've got our first ionization energy. So that's the amount of energy required to remove the first electron. So if we look at hydrogen in the first row, it's 1.3, and then in the heading there, it's times 10 to the negative third. So it takes 1.3 times 10 to the negative third kilojoules per mole. So we've got 1.3 there. Let's go to helium. We've got a first ionization energy and a second ionization energy. So the first one, the 2.4, represents the energy to remove that first electron. And then the 5.2 in the next column represents the amount of energy to remove the second electron. There is no third ionization energy because it only has 2 electrons. If we go to lithium, atomic number 3, notice that the first ionization energy is 0.5. That's a pretty small number because remember, lithium wants to get rid of that one valence electron so it can have the configuration of helium, the electron configuration of helium. Once it loses that first electron though, it doesn't want to lose another, so it's going to take a lot of energy to remove a second one. And that's why the energy really jumps when you go from the first to the second ionization energy. It goes to 7.3, and then if you go to the third ionization energy, so that's how much energy it takes to remove that third electron, it's a high number as well. Then let's look at beryllium. Beryllium is in group 2. So it wants to lose 2 electrons. So the first electron, to lose that one, only requires 0.9 times 10 to the negative third kilojoules per mole of energy. Not a lot. To remove the second one, it's 1.8. Not too much, because beryllium wants to lose those 2, but it doesn't want to lose a third electron. It's in group 2. It wants to lose 2. It doesn't want to lose 3. So notice the big jump from 1.8 to 14.8. Same is true for boron. Boron wants to lose 3 electrons. It's in group 13. So it requires a little bit of energy to remove the first one, 0.8, a little bit more energy to remove the second one, 2.4, and then 3.7 for the third one. So you'll see that trend as you go across the period. If we go down a group, let's compare. Hydrogen is in group 1. Lithium is in group 1 below hydrogen. Sodium is below lithium. And then potassium. So as we go down a group, we notice the first ionization energy here is 1.3, then 0.5, so it's getting smaller, 0.5, and again this is rounded, so it's not always super obvious, but our general trend as we go down the group is that it's getting smaller, the energy required to remove that first electron. And the reason that is because of the shielding effect. There's all those core electrons as you get higher and higher energy levels that are shielding the valence electrons from the nucleus, so it doesn't take as much energy to remove those valence electrons. Let's look at group 2 atoms. So that starts off with beryllium, then magnesium, and then calcium. So notice beryllium, 0.9, then magnesium below it is 0.7, and then calcium is 0.6. It doesn't take as much energy because there's more energy levels, so there's more shielding going on. So it doesn't take as much energy to remove those first electrons. Second electrons, same is true. 1.8, 1.5, 1.1. They want to get rid of 2 electrons. And as you go down the group, it requires less energy to do that because of shielding. But that third electron they don't want to get rid of. So that's a high ionization energy for each of these. So let's look at it a different way. If we have ionization energy on our y-axis, atomic number on our x-axis, and notice in our key up here, our first ionization energy is blue, second is pink, third is yellow. If we kind of categorize these elements at the bottom, 1 and 2, atomic numbers 1 and 2 are period 1, atomic numbers 3 through 10 are period 2, and then 11 through 18. So I could kind of just draw lines here for each of the different periods. So if we look at atomic number 1, 3, 11, and 19, those are all group 1 elements. Group 1 elements want to lose 1 electron. So look at how low their ionization energy is. They want to lose that electron, so it doesn't take a lot of energy for another atom to pull it away because they want to get rid of it. Let's do the same comparison for group 18. These are our noble gases. So atomic number 2 is helium, atomic number 10 is neon, atomic number 18 is argon. So notice that for the first ionization energies, the blue data points, the noble gases have the highest values because they don't want to lose any electrons. So it's going to require more energy to remove any of those electrons. Also notice as you go down the group for noble gases from atomic number 2 to 10 to 18, it doesn't require as high of a first ionization energy than the one before it, because there's more energy levels and more shielding going on. Let's go back to group 1, atomic numbers 3, 11, and 19. So that's lithium, sodium, and potassium. So notice group 1 elements, the second ionization energy is really high because they only wanted to lose 1 electron, not 2. So it's going to take a lot more energy relative to the first ionization energy to remove those second electrons. They don't want to remove them. They only want to remove 1, not 2. So still looking at these atoms, let's look at their electron configurations. Notice they all have their highest energy level as the S1 orbitals, right? It's 2s1, 3s1, 4s1. So there's one electron in the s orbital of the highest energy level. That's their valence electron. So if they get rid of those, what's missing here is they all form ions with a +1 charge. So when it forms a lithium ion, it has the same electron configuration as helium. Sodium ion has the same electron configuration as neon. The potassium ion has the same electron configuration as argon. So it's easy to lose that one electron, but now they have a stable octet or their full highest energy levels and such. So they don't want to remove any more electrons. Let's look at atomic numbers 4, 12, and 20. So those are in group 2. That's beryllium, magnesium, and calcium. So notice for the third ionization energy, they're really high because those are group 2 atoms. They don't want to lose 3 electrons. They only want to lose 2. So their first ionization energy, for example, for beryllium, okay, it's easy to lose the first 2. I just circled those ionization energies. But once they lose the first 2, it takes a lot more to lose the third electron. Same with atomic number 12, magnesium. The first one's easy to lose, low energy. It doesn't require a lot of energy to remove that. Same with the second, but the third is a lot higher, etc. We can look at their electron configurations. So there they are. Notice they're group 2. They all have the S2 configuration for their valence electrons. So if they lose those 2, they become ions, which again should say 2+. And they're happy like that. They don't want to lose anymore. So it's going to take a lot more energy to lose the third electron, and that's why that third ionization energy is really high for them. When you consider ionization energies and when is it easy to lose or when is it hard to lose, think of who is eager to get rid of electrons so they can become stable. Okay, they want to be stable. Think of their electron configurations, what would make them stable, which makes them happy. So let's review that then. Recall that when they have a full valence shell, they're going to be very stable. So that's our 8 valence electrons, S2p6. If they have full sublevels, that's going to be stable. So if they can achieve that, even though they can't get a full valence shell, that's going to be stable, not as stable as a full valence shell, but it's stable. If they have a half full sublevel, that's somewhat stable, and anything else will be unstable. So all these atoms want to achieve stability. So the top situation, they're the happiest. The bottom, they're not happy. They want to be stable. So when you think about ionization energies, think of who's eager to get rid of electrons. Write out your electron configurations to see what's going to give them the most stability. Will they be able to get a full valence shell? If not, can they get a full sublevel? If they can, that's going to be better than a half full sublevel. And if they can have a half full sublevel, that's better than everything else. So you got to think in those terms when you figure out ionization energies and the patterns and trends. All right, so the last trend we're going to look at, we've looked at atomic radius, ionic radius, ionization energy. Our last trend, the fourth trend, is electronegativity. And that is just the tendency for a bonded atom to attract electrons to it. A gentleman by the name of Linus Pauling quantified the electronegativity scale for us. And we now know that as you go down a group from top to bottom, the electronegativity will decrease. As you go across the period, the electronegativity will increase. Okay, so keep in mind what this means, because we will refer to electronegativity throughout the year. That's a tendency for a bonded atom to attract electrons to itself. As you go down, that electronegativity will decrease. Remember, there's a lot of shielding going on. that shielding effect as you increase in energy levels. And as you go across the group, you're adding a proton and electron. Each group you go across, there's going to be a greater attraction, so the electronegativity increases. So if we kind of have our periodic table, we can make this trend that the electronegativity value is the biggest over here, and then the smallest down here. And just so you know, noble gases don't have any values for electronegativity because they satisfy the octet rule, or helium has a full stable shell, so it's not going to attract electrons. So it has zero electronegativity. Actually, instead of saying it has zero negativity, it's not even considered. That's a better way to put it. So don't give it a number. We just don't even consider the noble gases when we talk about electronegativity. So essentially ignore those elements. All right, last slide. Let's go over those trends again. Atomic radius. As you go up and to the right of the periodic table, the atomic radius will decrease, right? So your biggest atomic radius is down here. The smallest is up there. We did talk about ionic radius as a trend. However, it varies as you go across the period. So it's not nice and easy to draw the table like we are doing for these three trends. So it's not on this slide. But remember, the +3 was smaller than the +2, which is smaller than the +1, which is smaller than the 0, and then the -1, -2, -3. That's essentially as you go across a period what the trend is. Ionization energy, this is essentially the opposite of atomic radius. As you go up and to the right, the ionization energy increases. So for atomic radius, it decreased. Ionization, it increases. And same is going to be true for electronegativity. It will increase. All right, thanks for watching. Have a great day.